Professor Schultz, Joshua Schultz.
Good morning.
Okay, sorry, Gennaro, you have to unscreen.
Pardon?
1 second, Joshua. Thank you. Okay, Joshua, you can share your screen. Perfect. Professor Schultz, Dichone and Co. Analytical model for 5-ply cross-laminated timber. Please.
All right. Well, thank you so much. Good afternoon or good morning from the west coast of the U.S. here. So what I'd like to do here today in the relatively short amount of time that I have is, rather than focus on all the details of the actual derivation of the model, which are in the paper, and I'd be happy to talk about, I'd rather talk about the context and the motivation for what we're doing here. So the real impetus for this is coming out of a partnership with industry. So it started probably 8 years ago while working at SOM on the Timber Tower. And then most recently, it's been developed in partnership with some of our local cross-laminated timber or CLT manufacturers located in Washington. So I'll be presenting on behalf of my colleagues, Dichone and Cope here. So for those of you who aren't familiar, cross-laminated timber is effectively a composite structure where the inner layers are orthogonal, laid up orthogonally to the other layers. And so oftentimes what you have 3, 5, 7, 9-ply structures. And so coming up with a series of design equations specifically for designers. So we're not looking for complicated numerical methods. What we're looking for are initial design equations that we can give to designers to improve our designs and give reduced material usage here. So what really spawned this was the idea that there's a real lack of design methods for practitioners regarding CLT panels. And that's important even at the lowest level, because if you look at a building, as soon as you go over 3 or 4 stories, up to 40% of your structural system is going to be in the floors, and up to 70% of that structural system for high rise. So you can make a lot of gains materially if we can dial in our efficiency on the thickness of those laminates or the different overall composition of those. So what we did here, and I just want to walk you through this briefly, is this idea using some of the basics of engineering. So if we look at the difference between concrete and CLT, and then if we look at the impact of our boundary conditions, that'll show you why we're focusing ultimately on a 5-layer composite beam model rather than a shell or a plate model for now. So if we look at a concrete model and we end up with a simply supported beam, or rather I should say a one-way slab that we can model as a simply supported beam. Everyone here I think has a good grasp that obviously your deflections are going to be significantly larger. And so what you can see right here on the screen is that what governs your design is actually designing for deflection. So you're stiffness driven. Whereas if we can move to a fixity, that boundary condition addresses our stiffness consideration. And now we're designing in the strength realm. And so if you look at that, right, this is a good example we always use in class. You have the ruler, you apply the load, you get a deflection, you clamp that fixity moves us from designing based on stiffness to moving us over to designing for strength. So that's a wonderful thing. So we thought we would take that approach for CLT. But what we find when we move over to CLT is that there are material limitations. So CLT, when we're pinned, we're in a vibration and or deflection realm, depending on where you're at. And so these are all for equivalent loads and spans and things like that. And when we move to our fixity, what we end up with is the reality that fundamentally this is a wood product. And so the way we design these wood products, of course, is that mass timber is remarkably resilient to fire. But the way we deal with that is that as fire is introduced, you end up charring those bottom layers. And so just intuitively, if you end up charring your longitudinal layers, even if you don't burn into that second layer is a transverse layer. So effectively what you do is when you introduce a 2-hour fire rating to a CLT material, you move from a 5-ply to a 3-ply. And so what that effectively does is now my design is driven by the post-fire strength of a 5-ply being equal to a 3-ply. And so the thought is that in this very specific scenario, if we can get additional strength out of the CLT, I can move from being governed by a post-fire strength design to an actual service design. And so now we're not taking an unnecessary penalty associated with the CLT product. So real quickly here, and we can talk about this, it's a pretty straightforward layup, no pun intended there. We've got a 5-ply. We're using a composite layering, so plain sections remain plain. And that's for each element, but not for the overall unit. So we're allowing those individual layers to rotate. What we're doing effectively is we're saying that these longitudinal layers here in the white are taking all of our axial tension and compression, or the preponderance of it at least. And then these inner layers here, these transverse plies, are taking the shear. And so what we're doing is we're using a composite model, and we're setting that up in terms of our strain energies. We're taking the variations for that. We're simplifying that all out through calculus. Through a whole bunch of bi-algebraic manipulation, we can end up with deriving the axial forces in each one of those plies. Once you have the axial forces, you can work those back into your overall displacements. And then what's valuable for the designer is we can take those displacements, convert those into our stresses, and now I can give the designer a closed form solution for the stresses at each one of the inner layers of these plies. So what we've done right now is we've taken that and we've accomplished that for a simply supported and for a fixed system. Now what we're doing is we're taking those series of relatively complicated closed form solutions and we're doing a series of best fits so designers can kind of plug and chug through those. And then we have just gobs of 3, 5, and 7-ply experimental data that we've been fitting to make sure that we have accuracy in our results. So with that, what we're going to do is we're going to deliver those best fit design equations for actual designers using that 5-ply model. And then eventually there's some desire there to expand that to some post-tensioning for a project we've got going on in Oregon here. So that really is the overview, the context and the motivation here. I did my best to try to keep it within the time, which is always a challenge here. What I wanted to do is just give everyone on the call sort of the context and the motivation, and I'd really welcome any additional thoughts here. If you have questions about the math, I'm happy to talk about that. I can talk about variational calculus probably longer than anyone wants to listen. So that's the overall thrust. And at this point, I just want to thank you for your time and for this opportunity, and then welcome any questions.
Well, thank you so much, Joshua, for the fascinating presentation. And are there any questions for this paper from the audience? A question, I have one. I have considered your preview material, and I want to ask you which is the effect to change the layer thickness in your multi-layer model?
Yeah, so what that goes into is one of the main assumptions which we're working on modifying, because right now it's a pretty simplistic approach, but it gets us within about 5 to 6% of our experimental results. And so what we're doing is we're assuming that all those longitudinal layers are taking the axial loading, and then the inner layers are only taking shear as a function of the shear stress. And so as you get thicker with that, two things happen. One is that you start to get some actual interlocking between the members, even though they're not side glued. And then the other thing that you have to take into consideration is you get rolling shear failures as you start to thicken those out. And so at that point, you've entered a new failure mode. And so there is a limitation really at the same thickness. You wouldn't want to go thicker with that. And the good news for that is that when you think about laying up these panels, the transverse plies as a structural engineer give me no real strength or no bang for my buck, right? So there's no practical reason to thicken those plies. In fact, what you'll oftentimes see with these CLT panels is when we go to thin CLT panels, we thin out the transverse plies because the longitudinal plies are doing all the work. But it's a great question because that definitely breaks down one of our fundamental assumptions in the equation.
Well, and the second one, very quick, are you going to consider also, if take place, of course, the lamination effect in your model between layers?
So that, yes, we are working on that in the analytical model. The reason that we're not too concerned with that right now is because as you go through the CLT manufacturing process, there's a handful of tests that you have to pass. In the United States, our governing standard is PRG 320. And there, one of the key things is delamination. And so you have to pass a series of very aggressive tests. And so those tests in the standard enforce failure in the wood, not in the adhesive. And so while we maintain those delamination in terms of the analytical model, again, practically the thrust of this is to get something for our design engineers, and that's intentionally not a mode of failure based on PRG 320.
Well, thank you, Joshua. Thank you again for your very important contribution to IWSS.